Hi, folks. Happy snow day. Hope you're enjoying the nice weather today. This is going to be a short recording, shortish. Trying to keep us up with our planned schedule for the course. So this week we're going to get started on chapter 3, and chapter 3 is about linear regression. A topic that you should have some familiarity with from whatever statistics class you took. So if you took it at Hope, these are topics that would have been covered in Math 219 or maybe even Math 215 if you took that course, or Math 311, 312. We're not going to spend a whole lot of time discussing this chapter using slides because we're going to rely a little bit on your background from your stats course there, and of course, if you need a review, the text actually covers this pretty well. So what we're going to do today is go through and hit some of the highlights, review some of the topics related to linear regression that are discussed in the book. At the end of today, we'll sort of leave things on a slide that reminds you of some additional topics that you would have learned about in your stats course that I think are also discussed in the book, that we won't discuss in lecture in here, but things that you should still review and think about, the things that you will need for the most part in this class. So our goal today is going to be to basically cover the first half of the slides. We'll review some of those concepts, and then we'll leave for Thursday what really is a new topic for us. First part of the slides is we go through and build linear models and take a look at them. We're going to be using kind of standard tools based on the LM function in R, and those are that's probably what you saw in your stats class. On Thursday, hopefully we'll be together in the classroom. We'll start to look at how to build linear models and fit linear models using functions in the Tidy Models package. And last week I mentioned that this is kind of overkill for linear models. The LM function works just fine, really. But as we move on to more interesting, more sophisticated, more flexible models in Math 313, we're going to want to use the Tidy Models package to build and fit and tune those models and test those models and so on. So we might as well learn some of that stuff in the context of models that we're already familiar with. That way we're not learning about new models and new techniques at the same time. We can just focus on the techniques there. So that's going to come on Thursday. Today we're just going to work with LM, do some things that are more familiar and review some concepts. All right, so I'm going to share my slides, and these slides are up on our Moodle page. And we'll get these started today, and we'll finish them on Thursday. Okay, let's do this here. Okay, all right. So you should see my desktop. You should see my slides here. Okay, all right. So we're gonna get started in the slides. Linear models, and you would have seen this in your earlier stats class, can actually be used for both prediction and inference. In fact, I mean, these are really the simplest models that we're going to encounter in this class. They're because of their simplicity, they're pretty straightforward. They're easy to understand, making them very interpretable. And the benefit of that interpretability is that we can use these models to make inferences. So we're going to start today by taking a look at a data set, fitting a model, using it for prediction, and then we're going to take a look at how we might use a model for that data set for inference instead. And we'll go through and talk a little bit about model selection, so predictor selection. in the context of that model that we're using for inference. And then we'll talk about how models are fit, right? How is a linear model fit in the first place? We'll review that using residual sum of squares. And then we'll talk about how model performance is measured. A couple different ways model performance can be measured for regression models. So that's even a little bit of review of some of the ideas from chapter 2. Okay, so that's where we're headed today. All right, so we're going to start with prediction with linear models. So linear models, like I said, they're our simplest models, most interpretable models that we'll talk about in Math 313. Compared to other models, we'll encounter other regression models. Remember, regression here is this general term that we use to describe models that are predicting a numeric response rather than a categorical one. So compared to other regression models, linear models are relatively inflexible, although there's things we can do to increase their flexibility. And they tend to have high bias, right? Because they're kind of a gross simplification, oversimplification of the true relationships between the variables that we're interested in. But they tend to have low variance, right? Low variance is good. High bias can be bad. All right, so low variance, again, means that if we had a different set of training observations, the model probably wouldn't change very much for a different set of training observations. So that's good. We don't tend to see overfitting, although that can definitely be a problem with these models. Like I said, you've seen these models before. You've explored their use in prediction inference. Everything you see here today really should be review. Okay, the data set we're going to work with is the car seats data set from the ISLR2 package from our textbook. You've already worked with this package in R, so you can play with this data set if you want. Build the same models we're building in here with the code that we're looking at in the slides. So remember, the slides that I'm using are just they're based on a Quarto document. So there's nothing that I'm doing here that you can't replicate pretty easily on your own. This car seat data set is made up. It's a simulated data set with 400 observations of 11 different variables. Each row in the data set, so each case, each observation represents a different store that sells car seats. Okay, so we've got 11 variables recording information about each of those stores that sells car seats. Okay, here's a quick glimpse of the data. So to make the data available, of course, we need to load the ISLR2 library. And then we can get the data set into our workspace by using the data function. Okay, and once it's there, we can refer to the data set by name, okay, by the car seats name. And this glimpse function, remember, is just a convenient way to view a data set, especially a fairly large data set, that presents the data in a more horizontal format. So each row in our glimpse here represents a column in the car seats data set. So the first column in the data set, and there's 11 columns altogether, the first column is sales. Okay, so sales, right, counts something like the number of sales. This might be in thousands of units or something like that of car seats at each of these stores. So you can see, right, the first store, right, in our data set has lower sales than the second store, and so on. Okay, there's 400 rows in the data set, right? So 400 different stores. Okay, there's things like advertising, right, which indicates how much they spend on advertising. There's population, which reflects how many people live in the area that the store is in. The price of the car seat. Okay, so this store is selling car seats for $120. This other store, which has more sales, is selling them for $83 and so on. Shelf loc, right? That's the location on the shelves that the car seats occupy in the store. So this first store, not only are the car seats relatively overpriced, but they're in a bad location on the shelves. Second store really is prioritizing these car seats, puts them in a good location, sells them at a good price, right? And they've got high sales. Let's see. And then there's some information about the customers here, right? So age, education. There's also information about whether or not the store is located in an urban setting or not, whether it's in the US or not, and so on, right? So some of the variables in the data set. All right, so we're going to build a linear model today, actually several linear models, using this data set to predict sales, okay, which is in thousands of units. And to begin with, we're going to use price, okay, which is in US dollars, urban, which has values yes or no, indicating whether the store is in an urban setting or not, and US, yes or no, whether it's in the US or not, as our predictors, right? So a numeric response, so we're doing a regression with 1, 2, 3 predictors, one of which is numeric, 2 of which are categorical, okay? We're going to start in the first half of the slides, what we do today, using the LM function. LM, remember, is short for linear model, like you may have seen in a previous stats course. Later, we're going to use those tidy models functions, and we're going to explore using this model both for prediction and for inference. Okay, so fitting a model in R, once we've got the data set in our workspace, is really easy using the LM function. Okay, so here's the structure of the LM command. All right, so we're going to create a linear model called LM1. All right, so we'll store the model object in the variable LM1. And we build that using the LM function. We've got to specify the relationship that we're interested in fitting a model for, linear model for. All right, so we use what's called a formula in R to specify that relationship. On the left-hand side of the formula, we have our response variable that we're trying to predict. In this case, sales. All right, and then there's a tilde. So you can think of tilde as saying in terms of. So we want to predict sales in terms of these predictors. So price, urban, and US. So those are our 3 predictors. And those predictors enter our model in an additive way. So at this point, we're not building a model that has interactions between any of these variables, right? They're just showing up in an additive way in the model. We'll look at how to include interactions in the model a little bit later. We'll review that. And then, of course, we've got to tell R and tell the LM function which data set we want it to look at. We want it to fit the model using the car seats data set. Okay. Once we fit the model, right, it lives in this object LM1, and there's all sorts of information there in LM1 that we could extract in different ways. One of the best ways to take a look at the actual model that we fit to our data is using the tidy function from the Broom package. Okay, so the Broom package is a tidyverse package, but usually it's not loaded by default when you do library tidyverse. So you can load it separately. Once it's there, you've got access to this tidy function, which is in the Broom package. So if I tidy LM1, right, I get a nice table, okay, that describes the model that I fit, right? So this is the regression output for LM1, this linear model I fit. Okay, the regression table has several columns. It's got rows for each of the coefficients in the model that I fit. The first row is the intercept. Okay, there's the estimate for that coefficient, right, for the model that I fit. Second row has my price variable. There's the coefficient on price. Third row, urban. There's the coefficient on urban. But notice here, this doesn't say urban. It says urban yes. Okay, so remember, urban is a categorical variable. And when we fit a model with a categorical predictor, what R is going to do is it's going to introduce some binary variables, indicator variables that have 0, 1 values. For a general categorical predictor with M levels, R will introduce M minus 1 indicator variables into the model. Both urban and US are binary categorical variables. Each one has 2 levels. And so R will introduce 2 minus 1 or 1 indicator variable for each of these binary categorical predictors. Okay, so it introduces an urban yes variable, okay, instead of replacing urban, and a US yes variable replacing US. So urban yes takes on one of 2 values, either a 0 or a 1. If the store is an urban store, this predictor will have a value of 1. If it's not, then this predictor will have a value of 0. So it kind of turns on and off, okay, in our model, depending on whether the store's urban or not. Same thing with US. If the store is in the US, US yes is going to have a value of 1. It turns on. If it's not in the US, it's going to have a value of 0. It turns off that term. Okay. Next column, right? This is more relevant for inference, which we'll talk a little bit later. But the next column is the standard error for that term, right? And what the standard error measures is we think of this car seats data set as being a sample from a larger population of stores that sell car seats. And if I were to randomly sample that population of all car seat selling stores, and I took a different random sample from that population with 400 stores in it, and then fit a model, right, that looks like this one, but just with that different sample, I'm going to get different coefficient estimates for that different sample of stores. If I take a third sample of 400 stores, fit a model, I'm going to get different coefficients. If I do a fourth, I'm going to get different coefficients. So my coefficients are going to vary from sample to sample. The standard error for each coefficient listed in the table is a measure of how much variability I would see from sample to sample for that coefficient if I fit linear models for different samples. It's really just the standard deviation of what those coefficients would be if I fit this model from sample to sample for different samples. All right, so the price coefficient, if I look at the distribution of price coefficients across different samples, the standard deviation of that, right, describing the variability of that coefficient, is about 0.00524. Okay, if I divide the estimate by the standard error, okay, I get a t statistic. So the third column here are t statistics, and I can do what's effectively a t-test using each of these statistics to test the null hypothesis that the value of this coefficient is 0 in the population. And when I do that t-test, I'll get a p-value here, right? So there's the p-value for each of those t-tests. And that p-value indicates, right, it gives me the probability that I would see a coefficient value at least as big as the one I observed if in reality the null hypothesis is true and the actual coefficient of the population's 0. Okay, so that's what that p-value is estimating here. Okay, you can see got really small p-values for the estimate or the intercept. Don't care about the intercept p-value. For price, fairly large p-value, 0.9 for the urban variable, and another small p-value like 4 in a million, 5 in a million for the US variable. Okay, all right, so there's our model, including a look at some of the other columns in the regression table. So let's focus on that first column and use this model to make some predictions. Okay, so based on those estimates, I can write the model out something like this. Okay, so the fitted model says that the predicted number of sales in thousands of car seat sales is 13.04, right? So that's my intercept. Okay, I was able to see it in a little bit higher precision, so I've got a less rounded version on my model, minus the coefficient on the price variable, right, which I can read from the table there, times the price of the car seat, minus the coefficient on urban yes. Oops, go back. Okay, right there. Times that indicator variable, urban yes. Okay, remember this has a value of 1 if it's an urban store, 0 if it's not, plus the coefficient on US yes, 1.2, times US yes, which turns on if it's a store in the US, has a value of 1, 0 otherwise. Okay, all right, so there's our model written out in a more helpful form, I think, than in the table. We can use that model to actually make predictions. So as an example of that, let's use the model to predict the number of sales in thousands for a store that sells car seats with a price of $120. That's in an urban location, stores in an urban location that's outside of the US. Okay, so I've got our studio over here. Okay, and it's going to be kind of small, so hopefully you can see this, but I'll talk it through anyway. All right, so to make a prediction using our model, right, I need to use the right-hand side here to make the sales prediction. All right, so I start with my intercept, right, 13.04. Okay, plus my coefficient on price, so minus 0.0545. Okay, times the price of the car seat, which in the problem statement is 120. Okay, so minus 0.02 times the value of urban yes. Well, this is an urban store, right? In the problem description, it says this is an urban location. All right, so that urban yes variable has a value of 1. So minus 0.02 times 1 plus my coefficient on US yes. Okay, so plus 1.20 times, well, this store is outside of the US, so times 0. Okay, so stores outside of the US, so it's the value of US yes is 0. Okay, so I've got 13.04 minus 0.0545 times 120, the price of the car seat, minus 0.02 times 1 because the store's urban, plus 1.2 times 0 because the store's outside of the US. All right, and I get 6.48. So my model predicts that this store or store these characteristics will sell 6.48 thousand, so 6,480 car seats roughly. Okay, all right, so that's how we use the model to make predictions. Of course, our other purpose, right, for building a model like this is to make inferences instead of predictions. All right, so we fit a model to data, right, from our sample. But we think of that model as actually being an approximation of what a model might look like if I fit a model using the entire population, like all the stores in the world that sell car seats. Okay, so the model we fit to the sample is just approximating that population model. And when we make inferences in statistics, what we're doing is we're using information from a sample, right, like our 400 stores, to try to say something about, make inferences about a population, all the stores, okay? All right, so what we're assuming here is that there's some relationship in the population in all the stores that sell car seats that can be described by this linear relationship here, right? So this is a very general form for a linear model, an additive linear model, no interaction here. You could write an interaction out this way though. But this model says that the predicted value of y, in this case sales, is equal to some intercept in the population, beta naught, okay, plus some coefficient, beta 1, times the first predictor, x1, okay, plus beta 2, another coefficient, times the second predictor, x2, and so on. And in a model with p predictors, the last term looks like beta p times xp, times the value of the pth predictor. Okay, all right, so our model says that the number of sales in thousands, right, for a store with predictor values x1, x2, all the way out to xp, right, is equal to, right, that sum, this linear combination of coefficients times predictor values, right, plus some error. So the last term just represents error. Okay, so the idea is that this relationship does not predict car seat sales exactly, right, but it describes the relationship between the predictors in car seat sales, but that relationship doesn't describe all the variability in car seat sales. So applying this model, we expect it to be off. We expect it to be wrong. We expect it to make an error because the values of those predictors don't tell us everything that we need to know to predict the car seat sales exactly. Right? So epsilon just represents the error. We usually assume that epsilon, if we look at all the observations, all the cases in our population, we usually assume that epsilon has certain characteristics, like it's normally distributed with mean 0, okay, and constant variability. So the variance or standard deviation of epsilon doesn't change for different values of y or different predictor values and so on. Okay, those are technical assumptions we make when we do inferences using regression. Okay, so a typical hypothesis test is really all about testing whether or not any particular predictor has an association with the response variable. So our hypothesis tests are phrased in terms of the parameter values for these coefficients, right? So the values of these coefficients in the population, the values of the betas, okay? So a typical hypothesis test, say for the ith predictor, is going to look like this. So our null hypothesis is that beta sub I is equal to 0, given that all the other predictors are already present in the model. Okay, so beta I equals 0, that means that with all the other predictors present, that if I increase the value of predictor I, then that doesn't tend to have an effect on y, on the response. Okay, so there's no linear relationship between predictor I and the response. There's no linear association between those two things with the other predictors already present in the model. Okay, so that's what we're testing here with the hypothesis test using a regression model. The alternative is a two-sided alternative typically, right? It doesn't have to be, could be one-sided. But in regression outputs, it's usually two-sided. The alternative is that coefficient in the population, that beta for the ith predictor, is non-zero. Okay, it may be negative, it may be positive, but if I change the value of x sub I, it's going to have some impact on y. And so there is some linear association between x1 and y with all the other predictors present in the model. Okay, so in addition to testing these hypotheses, right? Remember, in inferential statistics, we usually do two things, right? Depending on what we're interested in. We test whether there's maybe an association between two variables. That's what the hypothesis tests are related to. And we make estimates. And usually estimates involve calculating confidence intervals. So the other thing we can do is try to calculate confidence intervals for these coefficients to give us a range of values that are plausible values for these coefficients in the population. Of course, the two ideas are related. And if 0 is included in a confidence interval, that means it's plausible, okay, that the value of the coefficient is 0 in the population, in which case, because that's plausible, H0 is plausible, we can't reject the null hypothesis. So there's a relationship between hypothesis testing and confidence intervals. And you would have talked about that in your stats course. Okay, looking at the model, right? Looking at the model that we fit back here, pointed this out a little bit earlier. The p-value is huge for urban yes, like 0.936 is really close to 1. So we would conclude, right, that this coefficient is not significantly different from 0 in the population, right? The beta Right? In this case, it'd be beta 2, right? Because that's the second predictor in our model. We can't reject the null hypothesis in this case that beta 2 is equal to 0. It's plausible that there's no linear relationship between whether a store is an urban store or not and its sales. Okay. So as a result, we might want to simplify our model by dropping the urban variable from our model. Okay, and we're going to do that in just a second. Okay, but before we do that, for the sake of comparison between a model with urban and without urban, we want to take a look at some measures of performance of our model, how well our model fits the data. And this is a little bit confusing in R, at least I get confused. The glimpse function from the Broom package gives us, sorry, not glimpse, the tidy function gives us, from the Broom package, gives us the regression table we're after. The glimpse function, right, we can apply to the data set, like the car seats data set, we saw that back here, all right, just gives us a nice compact way to view some of the observations in the data and their values for the different variables in the data set. There's another function called glance. Okay, and if we glance a linear model object like LM1, this thing that we built using the car seats data, glance lists different model summary statistics, okay, for the model that we've fit. Okay, so let's look at some of these summary statistics for LM1. First statistic, probably familiar, is R squared, right? So the R squared value for this model is 0.239. That's the coefficient of determination for the model. The second statistic is the adjusted R squared. That's a penalized version of R squared that's adjusted for the number of predictors in the model. The idea here is that the adjusted R squared is going to give us a better idea of what R squared would look like on test observations. So observations that were not part of the training set, not used to train the model. So how much of the variability in those observations, test observations, would the model be predicted to explain? That's what our adjusted R squared is telling us. Although it kind of doesn't do a great job at that. We've got other measures that we'll use later that are better. Other things on here, right? We see our p-value show up. That's for the entire model, not for any particular coefficient. And then a couple other things we'll see a little bit later in the course are AIC and BIC. So AIC is AKEK information criterion, and BIC is Bayesian information criterion. So these are both also both measures of model fit that are also both penalized for the number of predictors in the model. Okay, but we'll see those later. All right. So we've got a way to look at how well the model is expected to, how well it's performing on the training set. Right, that's R squared. How well it might be expected to perform on the test set. That's adjusted R squared, or maybe AIC or BIC. Now that we've got that, it's possible to start comparing models to each other. Okay, so let's drop that urban term from the model, which wasn't significant anyway, right? It's plausible that this is 0, the p-value is huge. So let's make that coefficient 0. Let's drop that term from the model. So now we're going to fit an additive model with just 2 predictors, the remaining 2 predictors, so price and US. I'm going to call that model LM2. Okay, real creative with the naming here. And let's look at the coefficients for the model. All right, so there's the intercept, there's the coefficient for price, and then there's the coefficient for US, yes, that indicator variable for whether a store is in the US or not. Okay, note that with this model, all of the coefficients are statistically significant. Right, so we can conclude for each of these coefficients, there's strong evidence here, right, convincing evidence that in the population, these coefficients aren't 0. Okay, the betas aren't 0 associated with these predictors. We've got convincing evidence of that. Is it possible that they're 0? Yeah, but we've got very strong evidence that they're not. It's very unlikely to get coefficients this large if these coefficients are in fact 0 in the population. Okay, let's take a look at the performance of this simpler model. All right, so let's glance at LM2. You can see the R squared is higher after we drop urban. Actually, the adjusted R squared. The R squared should go down, right? Because we've dropped a predictor. We've lost information about our stores. So if anything, the R squared should go down. So let's compare. Let's look at the glance from LM1. It was 0.239. And now it's still 0.239, but maybe it's a little bit lower to 0.239 if we looked at this number in more precision. Adjusted R squared, however, right, was 0.234. Okay, we're not penalizing for as many predictors now. Our adjusted R squared goes up. So this model actually is expected to perform a little bit better on test observations than the other model is, even though that model had more information about the stores and it had this extra variable, this extra predictor to use. The idea here is that model with that extra predictor is probably overfitting a little, okay? If you look at AIC and BIC, 1863, 1879, right, compared to 1865 and 1885, right, those are both lower for this new model, okay? So based on these measures of model performance, right, that makes things look good, right, with respect to our decision to drop the urban predictor from our model. Okay, so we've gotten to a simpler model with just 2 predictors. Let's now complicate things a little bit. One of the things you probably talked about in your stats course is non-additive linear models. So in particular, models that include an interaction between 2 variables. So remember what an interaction means. Okay, so for example, if there's an interaction between price and the US variable, that means that the relationship between sales and price is different for stores in the US and outside of the US. Okay, so by including an interaction in our model, we're allowing for that to happen. Okay, allowing that relationship between sales and price to be different for stores in the US and stores out of the US. Okay, so let's build a model with an interaction. We're going to call this model LM3. And to specify an interaction between 2 variables in R, okay, instead of having a plus separating those variables, we use an asterisk. Okay, and this is actually a shorthand for in R for including those terms as main effects in our model. So it's like having price plus US plus the interaction between price and US. If we wanted to separate out just the interaction term, then we could do that with a colon operator inside our formula. So this is going to be equivalent to a model where the right-hand side says price plus US plus price colon US. If we look at the tidy version of the regression output, it's right here. You can see the coefficient estimates, okay, for this model that includes the interaction. You can see we've got this extra row down here, okay, that has our interaction term, okay. And then we've got things like the standard error statistic, p-value for these different model terms as well. Okay. Note, this is a little bit of foreshadowing. Right, we've got a gigantic p-value again, but this time on the interaction term that we just included. So we'll see kind of how that works out as we continue to explore this. Okay. All right. Let's see what the model looks like with an interaction expressed in this little bit nicer format. All right, so again, predicted sales is my intercept minus the coefficient from that table on the price variable, so minus 0.054 times the price of the car seat plus 1.3 times this US indicator variable. All right, we don't have the urban variable in the model, so that doesn't show up. And then here's our interaction term. So minus the coefficient on the interaction term, 0.000008, okay, times the product. So interactions in linear models show up as products, times the product of the price of the car seat and that US yes indicator variable. Okay, so that shows up as a product in our model. All right. So now let's get back to R, and we'll use this model to make a prediction. Okay, so let's use the model to predict the number of sales in thousands of units if the car seats are priced at 120 in a store located outside of the US. Okay, all right, so I'm going to go back into R, and what's my predicted number of sales? It's going to be my intercept, so 12.97, okay, minus 0.054, okay, times the price of the car seats, so times 120, okay, plus 1.3. Okay, this is not in the US, so times 0. Okay, so that predictor is not switched on. Minus 0.0008, that tiny coefficient, times US, yeah, so times 0 again, times the price of the car seat, so times 120. Right? So the only non-zero terms for this store that's located outside of the US, the only non-zero terms are actually just the first two terms in the model. Right? So it's 12.97 minus 0.054 times the price of the car seat. I've got zeros multiplying zeros as factors in the other two terms. Right? So the third term is turned off and the interaction term is also turned off. Okay. All right, so the predicted number of sales is 6.49 thousand or 6,490 sales for such a store. Okay. All right, so now next we're asked to use the same model to predict the number of sales if car seats are priced at the same $120 in a store that's located inside the US. Okay, so in the US, I'm just going back to what I just entered, and I'm going to flip the zeros, right, where I've got the US yes indicator variable. I'm going to flip those to ones. Okay. All right. So when I do that, I get a prediction of 7,694 sales, 7.694 thousands of sales. Okay. For a store that's located inside of the US. Okay. All right. So what's the difference in the model? When I'm in the US, my last two terms get turned on. Okay. So I add 1.3 thousand sales for being in the US. Okay, that's this term. And then I subtract a small amount here, okay, because I'm in the US, right, which changes the relationship a little bit between price and sales. Okay, so this term, right, turns on. USES is just a 1. Okay, so now price is going to have a little bit smaller impact on sales, actually a little bit larger, I guess, because it's negative, right? And the coefficient on price is negative. A little bit larger impact on sales because I'm in the US compared to outside of the US. Okay, so that slope is going to go from minus 0.0540 to minus 0.05058. So just a little bit different slope if I'm in the US than if I'm out of the US. Okay, because that part of the model is turned on. Okay, all right, so that's how prediction works with an interaction. Let's take a quick look at a plot of this linear model, right? So these are going to be the lines in the in this plot, along with the data that we're used to fit the model. So along with the car seat data. So I've got two predictors in my model, right? The price of the car seat, okay, which is easy to put on the x-axis here. And then the location of the store, whether it's in the US or not. Okay, I can represent that variable on my plot using a color. And so I'm going to plot points in red for stores that are outside of the US and blue for stores that are inside of the US. My model, remember, makes a different prediction for each group of stores. And in particular, because of the interaction, allows for the relationship between sales and price to be different between those two groups of stores. So what that means geometrically here is that the model allows the slope of the blue line to be different than the slope of the red line. Okay, the relationship between sales and price in the US, the slope of the blue line, that can have a different slope than outside of the US. So these can have two different slopes. The model we actually fit, remember those slopes are very slightly different. They differ by like 0.0008. Okay, so these slopes are very slightly different. These two lines are very nearly parallel. Okay. When it comes to making inferences about the interaction term, our null hypothesis is going to be that that slope on that interaction term is 0 in the population. What that would look like in our model is slopes that are actually parallel. So based on this picture here, it kind of seems like, right, that coefficient is, it's very plausible that that coefficient has a value of 0 in the population. We don't have much evidence here that these two slopes are different. In fact, they look really darn similar in this plot. Okay, so remember, if we look at the regression table again, so I'm going back here. Remember the p-value for the interaction term was giant again. It's 0.937. All right, so we have basically no evidence against the null hypothesis, no evidence that the value of that coefficient is something other than 0 in the population. Okay, so in the population, it's plausible that those lines are parallel based on our sample here, which shows the lines being pretty darn close to parallel. All right, so as a result, we would probably decide that we don't really need that interaction term and we drop it from the model. So our best model, based on the analysis we've done so far, is just that simple additive model that has price as a predictor and then the US variable as a predictor and no interaction, just an additive model. Okay, sticking with the interaction model just a little bit more, let's look at the model summary. R squared about the same. Okay, including the interaction didn't make the model really any more predictive. In reality, if we looked at this at full precision, we might see a little bit higher R squared. Adjusted R squared is lower now that we've included the interaction term because we've complicated the model, we've increased the penalty, we've upped the risk of overfitting a little bit, and so we get a lower adjusted R squared. Right? So our best model is that second model we looked at. Okay, so now just to change topics a little bit, we've reviewed how models can be used to make predictions. We've reviewed how models can be used for inference. We've talked about models with and without interaction. We've done a little bit in terms of model selection, although we're really only scratching the surface there. Now I want to talk a little bit about how these models are fit in the first place, and then also how we determine whether it's appropriate to do model-based inference with these models in the first place. And both of those things are based on residuals. Okay, come back to this concept of residuals. All right, so remember that a residual, right, each case in our data set, in our sample, has a residual associated with it. In fact, any observation, whether it's a test set or training set, has a residual associated with it. The residual just measures for each point the error that's being made by using the model to predict the value of the response for that point. Okay, that point has an actual value for y, an actual value for its response. It has a model prediction for that response. The difference between those two things, that's the residual, that's the error. Okay, the hat's kind of off, does this sometimes. So for the ith observation, the residual is specifically the difference between the actual value of I for that or y for that observation. Right? So the actual value, the observed value, minus the predicted value of y for that observation. And we indicate a predicted value by putting a hat over y. So imagine that shifted over to the left just a little bit. This is a browser issue with these slides. The residual sum of squares is what we get when we compute the residual for every point. Right? Let's say in our training set, square that residual. Residuals can be positive or negative. okay, depending on whether the actual value of y is higher or lower than the predicted value. But if we square the residual, of course, that's going to become non-negative. Okay, so we take the squared residual for each point, and then we just add them all up for all the points in the training set. If we're computing this for the training set. Okay, so it's the sum of the squared residuals. In least squares regression, the model that we're fitting, the coefficients are chosen to make the RSS as small as possible on the training set. Okay, so this is the thing that's being minimized. There's lots of possible values that we could choose for those coefficients. So which ones do we choose? We choose the ones that minimize the error in the specific sense of minimizing the RSS. Okay, here's a plot and some R code showing you how to get here, showing you the residuals for our preferred model for car seat scale. So this is the residual plot for the additive model using price and the US variable. Okay, our residual plot plots the value of the residual, so these are the E sub i's on the y-axis, against the predicted value, okay, for these observations. So I've got y hats on the x-axis and e's on the y-axis, okay? This residual plot shows the sort of characteristics that we want to see in a residual plot. Okay, so remember the model, first of all, is trying to minimize the squared residuals, so the squared distance from each of these points to the 0 line here. Okay, trying to minimize the sum of those squared distances. But residual plots are also used for diagnosing problems with linear models. To do inference with a linear model using traditional model-based methods like t-tests, and that's what is happening in our regression table, we have to make sure certain assumptions of those models are met. Okay. In particular, we want to make sure that the residuals are at least roughly normally distributed. Okay, so the way we evaluate that is we go to any particular fitted value on the plot, and if we take a vertical line at that value, okay, the residual should be roughly normally distributed along that vertical line, right? So maybe more bunched up at the center, a little bit more spread out as we move away from 0. Okay, so we're looking for that. There shouldn't be evidence of skew, like a bunch of points kind of spread out up above the red line or below the red line. So we're looking for things like that. We have that nice symmetric bell shape that we get with a normal distribution. The other couple things that we're going to check when we look at a residual plot like this are evidence of heteroscedasticity. Okay, so non-constant variability. So that would appear, if we had heteroscedasticity, that might appear as something like fanning in our data, where maybe for small values, fitted values of y, the points are all really close to this line, or this residual equals 0 line. And maybe they're a lot more spread out for large values, giving us kind of a triangle here, something like a fan. Okay, or maybe that fan goes the other direction, where we get large residuals for small predicted values and small residuals for large predicted values. Right? That could show up in a variety of ways. This residual plot does not show any evidence of heteroscedasticity. Okay, so this is good. We've got constant variability, or at least appears that we have constant variability independent of the fitted value of y. Okay, another thing we look at these plots for is any evidence of nonlinearity. So nonlinearity would show up in a residual plot if there's like a curve to the pattern in the residuals, right? And that curve can take a lot of forms, right? It could kind of wiggle around. It could look like a parabola, something like that. And that would also be an indication of a problem. That's an indication that a linear model may not be the right model to use to describe the relationships in our data. So we might try something a bit more sophisticated, or we might take one of our predictors and use its log, right, instead of the raw value of the predictor, or we might use its square or something like that. Okay. So those are the sorts of things we're looking at when we're diagnosing a linear model. Okay, a couple things I want to talk about. Now we've talked about residual sum of squares, RSS. There's a couple other, I think, kind of low-hanging things that we can connect to now that we've got that concept down and reviewed it. The first is the coefficient of determination, right? So R squared. We've seen R squared show up before. Remember, R squared on the training set describes the proportion of variability in Y in the response that's described by or captured by the model. So R squared takes on values between 0 and 1, right? If R squared is like 0.98, that means that the model is describing 98% of the variability in Y. If it's 0.1, it's only describing 10% of the variability. Okay, you've seen that before. R squared, right, can be expressed in terms of the RSS, the residual sum of squares. It's just 1 minus the ratio of RSS to TSS. Okay, so this 1 is like 100% of the variability, and then we're subtracting out, okay, the variability that remains unexplained, the proportion of variability that's unexplained by the model. So that's what this RSS over TSS represents. TSS is the total sum of squares. This is like the total variability in Y in our training set. That's computed by taking the observed Y value minus the overall mean Y value, squaring that, and then adding that up. So that's like the squared variability in Y. Okay, that's the total variability in Y. RSS, okay, is like the error. It's the variability that's left unexplained by the model. So if I take the ratio of the unexplained to the total variability, I'm going to get the proportion of variability that's not explained by the model. 1 minus that is the remaining variability. That must be the part that's explained by the model. So that's what R squared is measuring and how it relates to RSS and TSS. Residual standard error is another thing that's related to RSS that measures the quality of how well a model fits a data set. The residual standard error is just the RSS divided by n minus p minus 1. N is the sample size. P is the number of predictors in the model. Right, so this is like a degrees of freedom down here. Okay, and then I take the square root of that. Okay, so remember, RSS is like is measuring squared residuals. So I average those squared residuals by adding them up to get the RSS and then dividing by something that looks like n. Okay, so it's like an average squared residual, and then I take the square root of that to get something like a typical residual. Okay, so this is like a standard deviation, basically. Okay, for our residuals. Okay, called the RSE. Okay, we've already gone through this when we first saw the residual plot, right? So remember, in order to use the typical model-based hypothesis test, confidence intervals, we need to make sure that that we're meeting certain technical assumptions, and those are listed here. The only one we didn't discuss is those different methods always assume that our observations are independent from each other. So what that means in our car seat example is that knowing something about the sales for store number 1 in the data set doesn't give us any information about the sales for store number 50 or whatever, right? So the stores themselves are independent from each other. Okay, and then finally, I think that's finally, yep, finally, I've got a list of other things that we didn't really talk about in the slides today, but that are covered in the book that you would have seen in your stats course, or probably saw in your stats course. These are things that are still important topics related to linear models. So I still want you to know these things, but we're not going to go over them in slides. Right, you should understand what correlation measures, right? And Correlation is always between two numeric variables. All right, so you can, within a data set, you can calculate what's called a correlation matrix, which gives you correlations between each pair of numeric variables. You've seen that in some of the labs and APs so far. Multicollinearity, okay, is this this thing that arises when we're working with multiple predictors, where there might be a relationship between the predictors in the data. Okay, so this is different from an interaction. This just means that there's a correlation between some of the predictors in our data set, and that can affect things like p-values. You can have a model that performs really well with collinear predictors, but has really high p-values because we've got redundant information buried in the predictors in our model. We can measure collinearity with numeric variables using variance inflation factors. That's something that you should know about. There's other things you talk about in your stats course, probably like outliers, how to identify outliers, what are high leverage points. Okay, we did go through standard error for the slope. We did talk about t-statistic for the slope, okay, today in the slides. The other thing, at least in 215, 219, we talked about is a model selection process called stepwise selection. And there's two versions that we discuss in there, one called forward selection and one called backward stepwise selection. And the idea is for predictive models, these processes allow you to start with a bunch of predictors, potentially with the case of backward selection, and then systematically reduce the number of predictors while maintaining high performance for your model. Forward selection kind of goes the other way. You start with a minimal model with 0 predictors in it. Just predicts the y value for each point to be the mean y value for the whole data set. And then you add one predictor into the model at a time in a way that you're adding predictors to make the model perform better and better and better, and then you stop when you don't see those those performance gains. Okay, this is another topic that's also discussed in our textbook. Okay, all right, so we're going to stop there. On Thursday, we'll start talking about how to use tools from tidy models to start building linear models instead of LM. Again, kind of overcomplicating things, but we're going to learn how to use tidy models in the simpler context. So thanks for your attention, and I'll see you on Thursday.